One of the most interesting phenomena of special relativity is this concept of time dilation. The idea that time stretches out, time slows down from one frame of reference to another. That is, if you watch a frame of reference which is moving with respect to you, you will see that time runs slower for that frame of reference. Likewise, if somebody was in that frame of reference and they observed you, you would also appear to slow down. Seems like a paradox, but in fact, this is a consequence of the speed of light being constant, the speed of light traveling at c. So let's take a look at another thought experiment. I'm going to return to the boxcar, and we're going to look at how light will travel according to two different frames of reference for the same event. Now, again, let's just remember, regardless of the speed or direction, observers always measure the speed of light to be c, 3 times 10 to the 8 meters per second squared, meters per second. Speed of light's the maximum possible speed, so we can't go faster than that. In fact, we can't reach the speed of light. That is just what light can travel at. We can only travel in a frame which is going slower than that. So again, the consequences are clear. Clocks will appear to run slower in a frame of reference moving with respect to you. So here's what we have. We've got our boxcar once again. And in our boxcar, we have a flashlight. This flashlight is going to send a beam of light to the ceiling, hit a mirror, and then that light is going to hit the floor where there's another mirror. And I want to know how long is it going to take that beam of light to go up and then back down in my frame of reference if I'm sitting on this car, and in another frame of reference, which is moving with respect to the car. Let's say the train car is moving at a near relativistic velocity, and somebody's observing on the ground as the train passes. How would this light path appear, and how long would it take according to their frame of reference? So let's take a look at the two different situations. Up here we have situation A. We're moving with the mirrors. We're in the frame of reference, which is represented by the train car itself. We're basically going to be observing as if we were a passenger. The person watching the train from the outside was sitting by the tracks as the train goes by, would see the beam of light go up at an angle and then reflect back down. You say, well, doesn't light just go straight up and straight down? Well, it left the flashlight, okay? By the time it reached the ceiling, according to observer B, the top mirror had moved to this new location. And by the time the light returned, the bottom mirror had moved a total distance of the velocity times time. And V represents the speed of the car with respect to the ground, the speed of this other frame of reference with regard to the frame of reference that I'm observing from. So the first thing that we see here is that in the frame of reference moving with the car, the light only moves a distance of 2d. Okay, it goes up, then it goes down. But notice, for the observer on the ground, the light actually travels some distance s greater than d, okay? And then that light returns another distance s. So this is the hypotenuse of a triangle with a base of L and a height of d. That's going to be greater than d. Okay, so again, in frame A, we travel a total distance of, that should be 2d. I apologize for that. But again, in frame B, it's going to be greater than 2d. So how do we, determine this distance and how it depends on velocity? So again, if we see this, we can see that L is going to be equal to VTB, the time that observer B sees. V is the velocity of the frame of reference, or the car in this case. And again, D represents the height. So this hypotenuse, this distance s, and remember we travel s plus s, this distance s squared is going to be equal to L squared plus D squared. Now, we'll break this into two different parts, just two different triangles. We want to just look at the first triangle right here, which has a base of VT over 2. So S is here, D is here, VT over 2, that's VTB over 2 is down here. So let's just determine all this. S here is equal to C times TB over 2. The beam is traveling at the speed of light. It takes some time TB to go from the floor to the ceiling, and that time is TB divided by 2 because it's a round trip. D, we've already said, is C, but now in the frame of reference of A, TA, D is going to be C times TA divided by 2. And finally, L is determined by the speed of the train. It's V times TB divided by 2. So by the Pythagorean theorem, the hypotenuse squared is equal to the sum of the sides squared. We then make our substitutions. We get this equation here. And we'll multiply the entire equation by 4. 2 is in the denominator as 2 squared. So the equation reduces to this. Now I want to solve for TB on its own. So I'm going to put the TB terms on one side and put the TA terms on the other side. So I get TA squared is equal to TB squared 1 minus V squared over C squared. To get from here to here, I just divided the entire equation by C squared. That's why it looks a little bit different. And now when I solve for TB, okay, when I solve for TB, that's equal to TA. I'm going to divide it by this, take the square root on both sides, and I in fact see that the time that observer B sees the beam go up and down is equal to the time observer A sees the beam go up and down, divided by this factor right here. Okay, 1 minus V squared divided by C squared. And again, we can see this comes directly from geometry. This is the Pythagorean theorem that basically we've turned one side of the right triangle. Now we're looking at the hypotenuse, and the fact that the hypotenuse gets longer and longer and longer means, of course, that it takes longer and longer for the beam to travel in the B frame compared to the A frame. Okay, so that's time dilation, okay? Time dilation, time gets drawn out. If you're moving with a freight car, you see time just running regularly, okay? If you're moving in a different frame, it looks like time is slowing down for what's going on in that car, okay? It's taking longer because time is slowed down, and time has to slow down because the beam's traveling a greater distance. The only thing that stays the same in both frames is the speed of light. We can actually see this experimentally, and one incredible phenomena that demonstrates the special relativity law is the production of what are called muons. Okay, so this is a little complicated. Cosmic rays, which are basically junk thrown out from supernova explosions, we think they may also be due to quasars accelerating nuclei. But in any case, these very energetic particles hit air molecules at the top of the atmosphere. This leads to the production of a cascade of particles, the first of which are these pions. These are pi mesons. They're intermediate-sized particles. They're heavier than a lepton, like an electron, and they're lighter than a baryon, like a proton or a neutron. And the pions will then decay, and some of them will decay into muons. And this happens fairly quickly. A pion is a very unstable particle and decays rather quickly. Now, a muon is basically a heavy electron. It's an electron that's has the same charge, same spin, same properties, except for it's 207 times more massive than the electron. So it will decay into an electron plus a neutrino, an antineutrino. And this happens, again, toward the top of the atmosphere. Our atmosphere shields us from these primary cosmic rays. And we see that the time that goes by on Earth, okay, is different from the time that the muon sees. And I didn't correct this. It should be a v squared, by the way, folks. So when we're looking at this, that's a v squared. Okay, so muons have a half-life of about 2 microseconds. And if they're created 14 kilometers above the atmosphere, with that sort of half-life, even moving very, very close to the speed of light, they're not going to have enough time to make it to the surface. The speed of light is 3 times 10 to the 8 meters per second squared. Here we have a time, if we take 1.4 times 10 to the 4 meters, okay? And we divide it by 2.2 microseconds. They're not traveling fast enough to make it to Earth. So relative to an observer on Earth, the muons should have decayed already before reaching the surface. But according to special relativity, the muon will actually experience a different time, okay? Time will slow down for it, according to the observer on Earth. And again, it's 1 minus v squared over c squared. We'll shorten this up and call it gamma. That's going to be a very important number for later on. And effectively, the muons get a little extra life, okay? Time slows down for them, so they live a little bit longer than 2 microseconds, and they do make it to the surface. So once again, if we just use, regular Newtonian physics, if we just used Galilean mechanics here, we would see the muon created at the top of the atmosphere and then decay after traveling about 6.6 times 10 to the 2 meters. Now, this is half-life, so half of the muons would be gone by 6.6, 660 meters. And then another 660 meters, another half would be gone, then another half, and so on. So almost all the muons should be gone, but yet we detect a large number of muons on the surface. Why is this so? Well, again, according to special relativity, we're watching this muon in our frame of reference, and time is slowing down for it. So it is able to make it down to the surface in less than 1 half-life. So again, muons should not survive the trip, but due to time dilation, the time is slowed down in their frame, and thus their half-lives are made longer. They make it to the surface. And this is directly measurable. We can detect where the cosmic rays are creating the shower of particles. We actually have optical detectors that will watch these showers take place. We have the means of producing these muons. We can produce these muons in a particle accelerator, confirm that their half-life is in fact 2.2 microseconds, but they're created at these relativistic speeds. So at their very high velocities, in our frame of reference, time is slowed down for them. Now, if we wanted to look at this another way, we could say, well, let's go back here. For the muon, in its frame of reference, it's not traveling, 4,800 meters, okay? It's not traveling this really long distance. It's actually traveling a much shorter distance because in its frame of reference, the Earth is experiencing a length contraction. It's experiencing a smaller distance. Okay, let's go back to gamma. This gamma is something that we're going to be using throughout this chapter. And gamma is equal to 1 divided by the square root of 1 minus v squared over c squared. V represents the velocity of the frame of reference, which is moving with respect to ours. So for instance, when v is 0 or much less than the speed of light, gamma just becomes 1. In fact, if we plug in here, let's say 1% of the speed of light, 0.01, we square that, so that's 10 to the minus 2, that becomes 10 to the minus 4, times c squared. 1 minus 10 to the 4 is, 0.999999. We take the square root of that, and it even gets close to 1. Gamma is basically 1, even for like 1% of the speed of light, which is really, really fast. It's not until we get going at much higher velocities. At 60% of the speed of light, at 0.6 c, gamma increases to 1.25. And what that means is that for this moving frame of reference, this frame of reference moving to ours, if it's moving at 60% of the speed of light, what would take 4 minutes in our world, or 4 seconds in our world, okay, we'd multiply that by 1.25, is 5 minutes. 4 minutes becomes 5 minutes. At 80% of the speed of light, okay, it gets even more, 1.67, or basically 1 2/3, or I guess that would be, thinking about this, 5/3. So if we have 3 minutes, okay, we have 3 minutes, and our frame of reference is moving at 0.8 c with respect to us, that 3 minutes becomes 5 minutes in their frame. If we could take this to the limit where our velocity for our moving frame goes to the speed of light, gamma would go all the way to infinity, because here we would have c squared divided by c squared. This is 1 minus 1 is going to be 0. The square root of 0 is 0, and 1 over 0 is, of course, infinity. So this gets larger and larger. It gets asymptotically larger as we approach the speed of light. And again, here is how gamma changes with different speeds. Here is the percent speed of light, and we can see that at 1/3% of the speed of light, gamma is, really very close to 1. It's 1.000006. Okay, not until we get up around about 33% of the speed of light, 1/3 of the speed of light, that we see, more significant time dilations, like a time dilation of about 6%. Time would appear to go 6% slower. At half the speed of light, it's 15%. Okay, and as you can see, getting larger and larger and larger here, as we get closer and closer to C, we never reach C, but gamma just keeps getting larger and larger. Okay, so for instance, at 99.67% speed of light, our gamma would be 12.3, meaning that 1 minute in our frame of reference would take 12.3 minutes in that frame of reference. And here, if you just want to apply this to 10 minutes, you just multiply gamma times 10 minutes to see how the difference would be in different times of reference. And again, in our frame of reference, we're comparing how a clock would run in our time compared to how the clock would run on something moving like a spaceship. And again, 10 minutes on Earth compared to a spaceship moving with respect to us at 10% of the speed of light, it would take 10 minutes and 6 seconds. At 99.83% of the speed of light, 10 minutes would be, I didn't pick a very good one there, almost 30 minutes, almost half an hour. Okay,